In this case, one of the input and output pairs are utilized to connect input and output, and the second input is used for the external triggering purpose. Okay, so the problem which was with the inverter, like we cannot externally trigger, so that can be removed with the help of NOR gate or the NAND gate. Okay, so you can design SR latch either with the help of NAND or with the help of NOR. Both are possible. Okay, so these two additional inputs are basically utilized to trigger this logic. Okay, and we call them set and reset input. And based on this set and reset input, we prepared some characteristics table, and the table is something looks like this one. Like, so see here, if you see this equation, qt plus 1 is equal to r plus cube rt, something like that, which we can see here from the this diagram. But let us try to see what is the qt plus 1, what is the relation between qt plus 1 and then s and r. So that particular thing, we call it the characteristics equation. How the characteristic equation can be made, let us try to see it. Okay, if you can see here, if we can make the kmap for qt plus 1, so let us see how it will look like. Okay, to make this kmap, we need to go back to the previous slide. What was the exact value? So the kmap was based on the qt, s and r, where we have a 0 0 0 0 0 1 0 1 0 and so on. So we have total 8 possibilities, and out of these 8 possibilities, if you see here, the qt was 0 0 1 0 1 0 1 0. So let us try to make the kmap for this qt. So we need to remember this thing: 0 0 1 0 1 0 1 1 0. Okay, so let us try to put all these values in this kmap, so the values can be placed, and let us see how it will look like. Okay, so the value was 0 0. Okay, I forget the things. Let me go back to the previous slide. Yeah, one more thing that is very important. So let me repeat it again. If you see this case, 0 0 0, we are getting 0. 0 0 1, we are getting 0. So please write somewhere so that we can use it in the next slide. Okay, and for 0 0 1 0, we are getting 1. For 0 1 1, if we can see here, this is the intermediate state. Either it could be 0 or it could be 1. There could be racing. We cannot decide what is the output and what is the input. So this is intermediate state. So it could be either, so 0 and 0 is not possible. So either it could be the opposite in sense. So it could be 0 0, or it could be 1 1, or it could be 1 0 or 1 1. So this is what we call the race around condition. And this is the intermediate state. We cannot fix what state we are getting. So at this combination, like if we talk about 0 1 1, in this combination, output could be anything. This qt plus 1 could be anything. And then we need to consider it as a don't care. Okay, because we cannot predict what should be the qt plus 1 based on this one, because we have set and reset both. And if it is like this, then this qt plus can be 0, or it could be 1. It could be 0, it could be 1, and vice versa. So any of the 4 possibilities can be there: 0 0 0 1 1 0 and 1 1. So in conclusion, we can say that at this stage where we have 0 1 0, we can say these are the don't care conditions. Similarly, the thing will be applied at this case, 1 1 1. Okay, so here we have again intermediate state, so we can call them the don't care states. Okay, so considering the don't care for 2 cases, for this case and for this case, let us try to fill the kmap. Okay, so the kmap will be 0 0, and it was 1. This was don't care, 0 0 1 don't care, 1 0 1, and last one was the don't care. So this will be the final kmap which we can see here. Okay, so if we try to simplify this one, then we can see here. Let us try to make the pair. So the first we can make a quad over here. So this is possible. Okay, this is the chord. So if we try, and this is the first possibility that we can make the pair. Second one could be like we can have the pairing of this one with this one. So let us try to write it down. Okay, if we simplify this chord, we will get like, yeah, q will be cancelled out, and here I will get something like r will be cancelled. Yeah, so what expression I will get? Can anyone tell me?
S.
Yes, so qt plus 1 is going to be s plus, yeah, so from here I will get s, because if I simplify this chord, then I will get s, plus if I simplify this pairing, I will get qt, and then what I will get? I will get r bar. Okay, qt r bar will be the expression. So the qt plus 1 will be s plus qt r bar. Second thing, if we can go back to the previous slide, in the previous slide we saw in this one, the conditions, this condition and this condition is not acceptable. Okay, these two are not acceptable. So what it means? It means that this SR condition is not acceptable. If the SR will be 1 1, so in that case it will come to the indeterminate state, or this is not acceptable case. Okay, so this case and this case is not required. So what second condition I can see here? If you see here, SR are 0 0, then this is acceptable state. S and R are 0 and 1, then this is acceptable state. 1 0, this is acceptable state, and same is for this one. So if somehow we can, after seeing this one, how the logic looks like, if you see here, we have the combination 0 0 0 1 1 0 1 1, and I need this logic should be that should give something valid output, and this should not give the valid output. So can we keep one condition? If s into r are 0, then those conditions are the valid conditions. Let me repeat it again what I am saying. As I told you, 0 0 is the valid case, 0 1 is the valid case, 1 0 is the valid case, but 1 1 is the not valid case. So if I kept SR is equal to 0, so 0 into 0, that will give you 0, so that is valid case. 0 plus 1, that will give you the 0, that is valid case. 1 0 0, 1 into 1, S into R will become 1, and if it is 1, this is not valid case. So the second equation that we can keep while analyzing is like SR should be 0, the product of S and R should be 0. So this is important point. So the S into R is equal to 0. So these two are the important case or the characteristics equation for the SR latch. So this is the characteristic equation. Yes, please. Anyone has any doubt? Okay, so fine. So this equation, what we are seeing here, this is really very important, especially if you will design the counter and other things. Okay, so this is really very important equation. Okay, now let us try to see a few more things. So these equations, these two equations, we call it the characteristics equation for SR latch. Okay, now let us try to make the state diagram of this one. Okay, what state diagram says? I will recommend just please note it down, this one, because this is needed again. Okay, this is required. This is a required case. So we can make it, we can choose it. Okay, so please note it down, and then accordingly we can make the state diagram. Okay, because this is required actually. Fine. So if we can note it down, let us try to see. So here we have 8 combinations, 0 0 0 2 1 1 1 1, and accordingly I'm getting qt plus 1 like 0 0 1 0 1 0 1 0. So remember this thing, and yeah, some of the cases I don't care, so we'll also consider those things, no problem. Let us try to apply this thing. Okay, what we can apply, see here. Let us try to make the state diagram. If you see, we can have a two states for qt. Qt can have two outputs. Either it could be 0 or it could be 1. Okay, so the qt can be 0 or 1. There are two possibilities. So let us assume either qt or the past state can be 0 or the past state can be at the logical 1. Okay, so if you see the table, here we have a table like qt, s and r, and accordingly qt plus 1 is calculated, and there are possibility 0 0 0 0 0 1 0 1 0 0 1 1 1. Yeah, so let me write it. 1 0 0 1 0 1 1 1 0 and 1 1 1. And the qt is something like, if we can recall, the qt was given like qt plus 1 was 0 0 1 0 1 0 1 0. So this was the qt which we have calculated, because this table is required all the time, so I need to make it like this one. Okay, now let us try to do something. The qt plus 1 can have two options. And if you can recall here, the qt is like either it could be 0 or the qt could be 1. So let us consider the qt is equal to 0. Okay, now see the first case. Okay, first case is the qt is 0 and qt plus 1 can also be 0 if s is equal to 0, r is equal to 0. So if the qt present state is 0, so the next state can also be 0 if the condition is if s is equal to 0 and r is equal to 0. So let me write it properly. S is equal to 0 and r is equal to 0. Okay, so for this case, I will get the same output. Now let us consider the second case. If you see the second case, qt was 0, and if s is equal to 0 and r is equal to 1, I was getting the next state is again 0. So if s is equal to 0 and r is equal to 1, then I will get the same state here. Okay, now let us consider the third one. Third one is if s is equal to 1 and r is equal to 0, the qt plus 1 is switching to next logic, which is from 0 to 1. So 0 to 1 will be switched if s is equal to 1 and r is equal to 0. Okay, so this is how we can make this one. Next one is, next step, if you see, if 1 and 1 both are 1, then what will happen? Okay, if s is equal to 1, r is equal to 1, this condition is don't care condition, so we should not consider these conditions into the state diagram. So we need to avoid this one, because this is the not required case. This is not a valid case. So we need not to consider these two cases. This case and this case should not be considered. Only we need to consider those cases which are valid. Okay, so these two cases should not be considered while designing this state diagram. Now let us talk about this case. If you see this case, if q is equal to 1, qt is equal to 1 and 0 and 0, so I am getting the same output 1. Okay, so here I will get the same thing if s is equal to 0 and r is equal to 0. So I will get the same thing. Now next case is 0 and 1. So if 0 and 1 is there, then I will get if the previous state is 1, so the next state will become 0. So the next state will become 0 from 1 to 0 if s is equal to 0 and r is equal to 1. Okay, now the next case is 1 and 0. So if 1 and 0 kind of thing are there, so it will maintain the same state, because the previous state is 1 and the next state is going to be 1. So for s is equal to 1 and r is equal to 0, that will be maintained, means for s is equal to 1 and r is equal to 0, the next state should be 1 again. Okay, so this is how we can make the state diagram for SR latch. If you have any doubt, anyone, please let me know. I will explain it again how we are getting these things. So how this state diagram is made, if you have any doubt, you can ask the question. Okay, so I am giving 1 minute time to think, and let me know if you have any doubt on this.
Sir, can you say again what did you say about s equals to 1 and r equals to 1?
S is equal to 1 and R is equal to 1. Okay, so let me 1 minute. Any other doubts? Yeah, so please collect all the doubts, then I will tell you what exactly thing is. Anyone others has any doubt, then you can tell me. Okay, fine. So you are asking about S is equal to 1 and R is equal to 1. Which case? Which case you are asking? Can you repeat
that s equals to 1, r equals to 1 and q of t equals to 0.
S is equal to 1 and R is equal to 1 and Q is equal to 0. Okay, so you are talking about, yeah, this case. Okay, these two cases. See, if you can go back to the previous slide, these two cases, like this case and this case, is indeterminate state, which is not the valid state. This is not recommended. Okay, in any of the designing, these two cases are not recommended. Okay, so if these two cases are not recommended, so we will not consider these two cases for the state diagram preparation. Okay, so while making the state diagram, we will not consider these two cases. Okay, we will consider only these 6 states are the valid states. Okay, rest 2 states are not valid. Okay.
Yes, sir.
Because see, if you can recall this particular slide, I just told you the characteristic equation. So even though if I will consider those two states, this one and this one, this condition is not going to be satisfied, because the state diagram can be made for those states where we can satisfy these two cases, these two equations. And if you see this fourth one and the last one, this equation is not going to be satisfied. SR is equal to 0 is not going to be satisfied. And if it is not satisfying, then we cannot consider in the state diagram. Okay, got the point?
Yes, sir.
Okay, so this is all about the state diagram. Sorry, I removed one thing. S is equal to 0, R is equal to 1. Okay, so this is all about the state diagram for the SR latch. Now, yeah, this is also equally important, so you should understand the things. Now let us consider the next and very important thing, which is the excitation table. And this excitation table is really very important, especially if we are planning to design a counter. Okay, so let us try to see how we can make the excitation table for the SR latch. Okay, excitation table indicates what is the status of past value, what is the status of present value, and or the present value or the next value, and based on that, what will be S and R. Okay, so we have to come up with the value of set and reset inputs based on past and present inputs, or the present and the future input, whatever we can say. Okay, so simply I just wanted to tell you, like, I need to consider qt and qt plus 1 to define reset and the set. So if I'm considering like this, so we can call them, these are the excitation table for the flip-flop. Okay, so let us try to do that. Okay, so here we can have qt, which is the current past output, and qt plus 1 is the present output. Okay, so if, like, we can have the 4 possibilities in the qt and qt plus 1. So let us try to prepare this table. This table is going to be really very important. So 0 0 0 1 1 0 and 1 1. So these all are the possibilities. Now let us try to see. If q is equal to 0 and qt plus 1 is equal to 0, means q is equal to 0 and the qt plus 1 is equal to 0. So present and past inputs are 0. Then we are getting these two cases. If you see here, present and past both are 0, and we will get like S is equal to 0 and R is equal to 0, S is equal to 0 and R is equal to 1. So we can say S should be 0 and R can be anything. Either it can be 0 or it could be 0. This condition is going to be satisfied. Let me repeat again what I said. Here, if you see this loop indicates present input and the next input, or the past and the present, both inputs are same. Both outputs are same. Like qt and qt plus 1 both are same. Okay, and for that we have two conditions. The first condition is s is equal to 0, r is equal to 0, and second condition is s is equal to 0 and r is equal to 1. So if we closely see this one, so we can say we can keep s is equal to 0, but r can be anything. Either it could be 0 or it could be 1. If I have kept s is equal to 0, so the qt and qt plus 1 both will be logic 0. So this is how we got s is equal to 0, r is equal to cross. Can anyone tell me like what are the other cases for 0, 1? So the present is 0 and next one is qt plus 1. So we need to consider this one because we are moving from here to here. This is the present, this is the next. Okay, so for that we have the case s is equal to 1. Okay, so if you see here, s is equal to 1, r is equal to 0. Now please tell me for other two cases. What will be the output for other two cases?
Sir, s equal to 0 and r equal to 1.
0 and 1, absolutely correct. What about the last one?
Sir, don't care 0.
Don't care and 0, absolutely correct. Okay, so this is how the excitation table looks like. Okay, yeah, I think I made one mistake here. There is some problem. This should not be the input, this should be the output. Okay, and this should be the input because n, s and r are the input, and qt and qt plus 1 are the outputs. Okay, so this is the relation between output and input combinations. Okay, so this excitation table is really very important. Okay, so if you have any doubt, you can ask the questions, otherwise we can move ahead. So as of now, we have studied about the SR latch, where we consider the cases like simply there is no clock pulse. Okay, but sometimes if you want to make it synchronized, in that case gated SR latch is really very important. Gated SR latch means we need to control that SR latch with the help of clock pulses. So if somehow we have added some clock pulses, then yeah, so this is the circuit what we already know. This is the circuit diagram for the SR latch, where we have one set input, reset input, and the Q and QT bar, and we have made it with the help of NOR gate. Okay, but if I want to make this logic, yeah, this is simply the SR latch which we have already studied before. Okay, and if I want to make this logic as a clocked control or gated SR latch, then what can be done? What we can do? We can simply add two AND gate, and the set and reset inputs are like this. Reset and set inputs are these ones. Okay, and the clock that will decide how to control this one. See here, let me repeat it again, how it can be done. If we are not considering these portions, okay, if I am not considering these portions and I'm considering this is the reset and this is the set, okay, and this is the QT and this is the QT bar. Okay, if this is the case, I'm not considering this part. Okay, so the simply based on the reset and the set input and the QT value, this QT plus 1 will be reflected, and the QT plus 1 will be reflected, but it will not be controlled with the help of clock. Because see, if there is a change in R or S, definitely immediately QT or QT plus 1 will be reflected. Let me repeat again what I'm saying. Suppose I have a R and S only, I do not have this clock control. So if there is a change in set or reset, any point of time, immediately the QT plus 1 will be reflected. It does not depend what is the clock, what is the status of clock, whether the clock is activated or not. So to avoid this problem, we need to make this circuit clock control. If the clock is high, then this set and reset should pass and that should activate the logic. Otherwise, it should not activate. Okay, so So for that purpose, we need to use this gated SR latch, where this clock pulse will be responsible to decide whether I have to pass this reset or set or not. Okay. Otherwise, suppose if clock, let me assume if clock is equal to 0, in that case, this will be 0 and this will be 0. So the QT plus QT is nothing but this will maintain the previous state. Okay, because the set and reset are 0. So the QT plus 1 is nothing but this is equal to QT. So this will maintain the previous state. So the output is not going to change, even though there are change in the set and reset, but if the clock is not activated. Okay. Now, if clock is equal to 1, if the clock becomes 1, then what will happen? Now, if there is some change in the R and S, that will be reflected at these points, and the output will be reflected again. So the important point of consideration here is that now initially the SR latch was uncontrolled. Okay, if there is some change in the set and reset, immediately they are going to be reflected at the output. But now it is controlled by the clock. This clock will be responsible to decide whether I have to change the output or not. If this clock is equal to 1, then the output will be changed based on the inputs S and R. Okay. And if the clock is equal to 0, then even though there are some changes in the set and reset, that is not going to be reflected at the output side. So this is how this gated SR latch is important, and the clock is mandatory in any of the design. Okay. So let us try to make the truth table for this case. Okay. How we can make the truth table? Suppose I have a set and reset inputs. Okay. These two are the reset inputs. We have a clock pulse, and let us try to see the QT plus 1, which is the next output. So we can have the two things. Let us assume if clock is equal to 0. Okay. If clock is equal to 0, then whatever the condition of set and reset is there, it does not matter. Okay. QT plus 1 is nothing but this will maintain the previous value, which is the QT. So if clock is equal to 0 and set and reset or anything, the QT plus 1 will be same as the QT. Okay. So what it means, it will indicate the previous value. Okay. So previous value is going to be reflected. Now let us talk about the clock 1. If clock is equal to 1, then we can have the 4 possibilities. Okay. So let us try to see 1, 1, 1, 1. Clock is 1. So I can have 4 possible input cases: 0, 0, 0, 1, 1, 0, and 1, 1. If it is the case, then if clock is equal to 1, then 0 and 0, and we know that 0 and 0, that simply indicates the like if it is 0, 0, then what will the output? Can anyone tell me? 0 and 0, what does it mean?
The same output QT.
Same, yes, QT plus, it will be maintained. It will hold the logic. Okay, previous output. Okay, so previous value, simply it will be the previous value. Okay, yeah, it will hold the logic. Yeah, so it will hold the same as it is. Okay, now if it is 0 and 1, we know that 0 and 1 means set is equal to 0, reset is equal to 1. So output is going to be reset. Okay, because reset is activated here. If set is equal to the, yeah, so this is what we can say, this is the reset the output. Okay, next 1 and 0 means we are setting up. So it will set the output, which will give you the 1. And 1, 1 means indeterminate state again. Okay, so 1 and 1 means like this is the, we cannot decide what is the output. So indeterminate state. Okay, so this is the truth table for the gated latch. If you have any doubt at this point, you can ask the questions. Reset is 0 and set is 1. It means the set will activate. So it will set output to logic high. Okay, it will set output to the logic high. If set is equal to 1, reset is equal to 0, means output is going to set at 1. Got the answer? Okay, so this is what the gated SR latch works. Okay, now let us further extend the analysis. So suppose I want to make this SR latch or SR flip-flop. Yeah, one very important thing. The logic which we have designed over here, whatever we are discussing over here, all this logic, this we are calling it the latch. Okay, but if there is an involvement of clock, then in combination we can call them the flip-flop, and this is the difference between latch and the flip-flop. Let me repeat it again. If there is no clock pulse, then we can call these kind of designs are the latch. These all are the latches. They are able to hold the logic. Okay, but if you have clock pulse associated with that logic, so the complete one, this we can call it the latch, and the half portion we can the complete one we can call it the flip-flop, and the half portion we can call it the latch. Okay, so this is the latch and this is the flip-flop. Okay, so this is the difference between these two. In more detail I will tell you what other differences are. Okay, so please wait, but for now you should know, like after including clock, what we call this circuit. So this circuit is nothing but this becomes the flip-flop. Okay,